So in my previous video, I was explaining to you about what is Big Bang, and I introduced you to the whole concept of Big Bang and the expansion of universe. And we also saw what is a cosmological principle, and also we looked into the Hubble's law and what did Hubble identify, and also we calculated the age of the universe. If you haven't seen it, please go to the link in the description. I've put I'll put the links for the previous video in the description below. And also, if you haven't seen my earlier videos, which is like on the fundamentals of astrophysics or astronomical instrumentation, please follow our channel, and the links will be in the description below. So please do follow for more such videos and content. So now that we spoke a little bit about what is Big Bang in general, how did it happen, what motivated us, and how did we end up in this whole scenario called Big Bang, right? So now we know that, okay, there is Big Bang happened, and there's like expansion in the universe, galaxies are receding away from us at a rate of 70 kilometers per second per megaparsec, and so on. So we know all these different aspects to it. Now let's look further in, like, what happened right after that Big Bang, right? What happened right after that initial explosion? So I'm going to take you through this video. I'm going to make it more like a journey of what actually happened in the first minutes, from the very first minute to slowly we'll get into all the way to the present. But let's start with the first epoch. So in the first epoch, as soon as the Big Bang occurred, what happened was the universe was just a soup of, like, it was just fully pure energy, and well, from the whole concept of E equals mc squared, right? Now this slowly condensed after the first 3 minutes after the Big Bang into matter. By matter, what I mean is quarks and leptons and so on. They were all, like, the energy condensed into matter. Okay. Now, few minutes down the line, these quarks and leptons, 2 up quark and 1 down quark, they formed the proton, and 2 down quark and 1 up quark ended up forming the electron and the neutron, and so on, right? Now, once these fundamental particles were formed, then you slowly, had you were in a soup of fundamental particles. Now, from this soup of fundamental particles, one proton, one electron started orbiting a proton. Now, this is when the first hydrogen atom was formed. And now, once the first proton captured an electron, boom, hydrogen was in the universe. Like, more protons started capturing electrons, and we had hydrogen. That's where now the universe was a soup of fundamental particles. Now it's just a huge cloud of hydrogen, and the temperature is still high. So what happens is it captures an electron and then it loses it because of the high temperature. Like, it can't hold it because the energies are super high, so an electron can escape easily. And then the universe kept expanding, and as thermodynamics says, as the pressure goes down, the temperature also goes down. As the temperature goes down, the universe started cooling and cooling and cooling and cooling. So now we were left with a bunch of hydrogen. But was it all hydrogen? No, actually not. While it was cooling, certain hydrogen atoms started fusing with each other because the pressure and the temperature was tremendous, right? Certain hydrogen atoms started fusing with each other to form helium. So there was a little bit of helium over there. And after helium, there was also lithium that formed. So there was like a little bit of what we call as the Big Bang nucleosynthesis. Whatever happened, whatever is going on sun right now, right? It was going on in the universe back then. Okay. Now this is the first ever atoms and elements that were just created. Now this is just like the first few seconds to few thousand years in the universe, right? Now, okay, now we are, now the universe expanded, the universe cooled down, you have hydrogen, you have helium and so on, but here's a big problem. There's no light. The universe was dark. Why? Well, how can we create light? To create light, I need to emit a photon from an atom. To emit a photon, I need to excite an electron, or I have to do something like, say for example, I have to have a magnetic field and I have to let a particle go through the magnetic field to emit synchrotron radiation. There was nothing. It's just a whole big cloud of neutral hydrogen atoms. Majority of them was just hydrogen, right? It was like a whole big cloud of just neutral hydrogen atoms just sitting there doing nothing. Now the universe was just that. Now, I mean, there were some photons that were created, but there weren't anything. There were zero photons at this point, and this is what we call as the dark ages. Now, dark ages means, yeah, the universe was dark. There was no light. So now you let the universe then continued cooling down further and further and further and further. Then there was something that happened in between, what we call as the epoch of reionization. That is, this neutral hydrogen somehow got ionized. Now, what do I mean by ionize is I have to kick the electron out of the atom. Then, well, I'm going to create H plus, like hydrogen ion or electron, right? So this ionization to happen, well, it needs some external force that has to do it. So who did this ionization? Now, this is a bigger question that is still being researched on. So this entire EOR is still going on. The work is still going on. One such thing was what we call as the first stars, or the population 3 stars. So how did everything form from here, right? So I'll get to the population 3 stars and the first stars. It's up there, but the universe got reionized at this point. So there was electrons. I mean, so basically, like at this point, the universe expanded enough. So it wasn't just neutral hydrogen, but then it was just like, okay, let's say I have a hydrogen atom here. Say I have another hydrogen atom, a third one. This was basically the universe. One proton and an electron. Let me just add a few more. This was literally our baby universe, right? With just one proton and an electron going around, just a soup of hydrogen. That's it. Now, what happened is, let's say like if I excite or if I ionize one hydrogen, I'm going to emit a photon. I'm going to emit a radiation out of this, right? Now now if I look at this point, in the previous video I said, if I look at 13 billion, 14 billion years from now, I'm going to look at 13.7 billion years in the past, right? That means I'm going to see this photon that came out of the first hydrogen. Well, the problem over there was the universe was super packed. Okay, even this is like super much of a space over here. The universe was just super packed with all these hydrogen atoms. So as soon as a photon gets emitted from one atom, the next guy captures it. And this electron goes into its excited state and it emits another photon. That is captured by the other guy. Okay, so the mean free path, that's what we call it as, right? The mean free path. The mean free path is the average distance that a particle can take. The mean free path was super small that the light couldn't just escape out of there. Now, the universe had to still go further. Now, the particles were still moving around, and like an electron gets excited or ionized, it emits a photon, another guy gets captured. This story just went on and on and on. And the mean free path was super small back then. And then the universe expanded further. Now, as the universe expanded, all these guys started moving away from each other, right? That means now I have enough mean free path around with me that the light can finally escape out. The photons can escape out before getting hit by another hydrogen atom. Now, this took about 350,000 years or 350,000 years from the moment of Big Bang. Now, I can show you a picture of it here. That's what we call as the cosmic microwave background radiation. So this is what we call as the baby picture of the universe. The way they identified this, again, this is like another stress back on the cosmological principle again. The way it happened was there were like two people, Penzias and Wilson. They were working in this place called Bell Labs, okay, in USA. And they were looking at they were trying to perfect an antenna and a communications antenna. And they were like, they were getting one particular in one particular frequency, they were getting a strong signal. And wherever they point the antenna, the signal was still super strong. And it was just the same thing in one particular frequency in microwave part of the spectrum. And wherever they looked, they saw the same strength, and it was a super strong microwave signal that they were getting. And they weren't sure where it is from. They thought it could be something with the antenna. They fixed the antenna. Still they heard it. And then they thought, okay, maybe some pigeons did some droppings over there. So then they cleaned up the antenna. Then they were pointing again. Wherever they pointed, they got the same noise, the same signal. And I mean, if you get something like that, you always think that it's your instrumentation's fault, right? Exactly like what Penzias and Wilson did. And then after a while, that's when from the cosmologists, they were expecting if the universe was expanding. Now at this point, okay, the universe would have been super hot, right? Now if I give it 13.7 billion years of expansion and cooling, where should our universe be right now? What is the temperature of our universe? Now the current temperature of the universe is 2.7 Kelvin. So now if you look into the emission of so every light has every temperature emits light in a certain wavelength. I would have told you about this in my previous series. Now say the room temperature that's around us, 27 degrees. This we actually emit light in the mid-infrared. So 27 degrees is around 10 micron is the wavelength. So that's where we emit light at. So the hotter we are, the shorter is the wavelength. The colder we are, the longer wavelength we emit. Now the universe is at 2.7 Kelvin. And that means I'm actually going to emit light in the microwave part of the spectrum. Now this microwave emission at 2.7 Kelvin was what Penzias and Wilson heard that time. And I said another fact was wherever they pointed, the signal strength was point on straight. It was always that value. So that's why they were always suspecting it's not something that is an external source, but it was some instrumentation fault. But actually, that was a validation to the cosmological principle. Wherever they pointed, they got the emission, the same strength of emission at the same wavelength, at the same frequency. Now that's because the universe was isotropic. Whichever direction you see, it was 2.7 Kelvin. Okay? And then in 1990s, they launched a satellite called WMAP. Now WMAP made this picture of the cosmic microwave background. Now in WMAP, they were able to resolve a little bit more information in the entire cosmic microwave background. So it wasn't all isotropic and homogeneous. There were some differences. Now this, again, I have to insist that this light, this image that we see, right, as the cosmological, as the cosmic microwave background, this cosmic microwave background image is what we call as the baby picture of the universe. These are the first photons that could escape. They were all trapped between hydrogen atoms, right? What you see in that image is the first photon that escaped out of it, because the mean free path was long enough for the particle to escape. So this was the very first photon that came out. So that's why we call this the baby picture of our universe. Now, when you resolve it with Penzias and Wilson's radio telescope, you will see a homogeneous 2.7 Kelvin. But what they did was they built a super precise instrument for WMAP, where they realized that there is the universe, if it was homogeneous and isotropic, right, and it's expanding isotropically and whatnot, how did we end up the way we are right now? That means everything should be homogeneous and isotropic. If I see a sun here with an earth right next to it, if I look one light year away, I should see another sun with an earth right next to it. If I see another one light year away, I should see another sun and another, and everything should look exactly the same, right? We all should have been copies of each other. I shouldn't have like Betelgeuse that's a red star where a sun is a yellow dwarf. I shouldn't see three different shapes of galaxies. Even like all these nebula have these shapes and structures. Even if you look at galaxies, they are at different places. I shouldn't see it. I should see one uniform distribution, right? Everything should be the same. Everything should be exact copies of the others, right? Well, that's not how the universe is. The reason behind it was that it wasn't completely homogeneous. There was a little bit of difference. So why or how did this happen? So what happened was, around this time, there was what we call as baryonic acoustic oscillations. That is, now here, this is again like a huge chunk of gas, right? This is the entire universe. What makes up all the galaxies and stars and planets and you and me, everything was in the soup back then. Everything that's in my hands or like, you know, on this marker or on the board, were a part of this story back then, right? So we were all part of this. That's the coolest part of this. We were all made of the same stuff that interacted out there. It's the same thing. So that means like, how did it like, so what happened around that time was, there was like some small temperature differences to a matter of 10 to the minus 5 Kelvin. 2.7 Kelvin, okay, this is today, right? There was like a small fluctuation of 10 to the minus 5 Kelvin. That small fluctuation, that small temperature difference is what you see as the difference in the cosmic microwave background image. And that difference is that made the entire structure of the universe that we see here today. This 10 to the minus 5 difference is like, how do I put it? It's like if you go onto outer space, right? About like, yeah, if you travel like all the way to outer space, about 10,000 kilometers from Earth, and you're looking at a small 1 kilometer bump. That's how it is. Or it's basically you're trying to focus on an anthill from the top of a mountain. That's how much is the difference, is this 10 to the minus 5. That tiny difference is what that made the structure that you see around today. And now this is what we call as this was created because of baryonic acoustic oscillation. That is, now all these atoms were all freely moving, right? That means at some point when two atoms are nearby to each other, the pressure in that area is going to increase, which means the temperature is going to increase. Laws of thermodynamics. The gravity is going to pull these atoms, like these hydrogen atoms together, but the temperature and the pressure is going to increase. That means as the pressure increases, they move away. Gravity pulls them in, and then temperature rises, pressure pushes them, it moves away. So it keeps doing this. Now this is what we call as baryonic acoustic oscillation. Now thanks to that one tiny atom, hydrogen atom, which refused to behave right, 1 in 10,000 atoms refuse to behave. Thanks to that one atom that is in 10,000 is why we are here today. So that one atom that refused to behave caused this 10 to the minus 5 anisotropy. Now, well, I spoke about isotropy, now I'm talking about anisotropy. Yes, we had that 10 to the minus 5 difference. And this 10 to the minus 5 difference is what you see on the cosmic microwave background. And this caused small density pockets, really small density pockets. Now these small density pockets created a small bump in the gravitational potential. And these small bumps in the gravitational potential was what that accreted all these material together to form galaxies and everything that you see around us. Now, I can go a little bit more into detail about this in the next videos, but I just wanted to like give a quick overview around this. So with that being said, yeah, I could also like explain to you what happened during this epoch of reionization. How did the first photon got like from the dark ages, right, where there was no photon, how did the first photon came out? And now I spoke about the cosmic microwave background and all the way till the first baby picture of the universe, right? In the upcoming videos, please do subscribe. I'll explain how did we reach to our current structure of the universe from this baby picture. So there are some simulations that I have built. I'll share it with you. We can look into that together in the upcoming videos. And please do subscribe to be in touch. Thank you.